In a fit of insomnia, I wrote a little program, a little script that converts a rational vulgar fraction, like a on b, where these are both integers, into a continued fraction. So something like 7/11. There you go. 7 is less than 11, so the integer component is 0. And then 1 on 1, 1 on 1, 1 on 1, 1 on 3, and then it terminates. And all of the examples I've tried work. So I think this probably works in general. So what it does is you take in two integers. Well, it converts them to integers. So yeah. The first one you give it is the numerator. The second one is the denominator. And this is all managing it. This one, so it's derived from the first approach that I did. It took floats. It took one float, and it would turn that into continued fractions. The problem is the resolution was poor, so even something like 3/7 would end up with a bunch of trash on the end because it just saw it as like a really large integer divided by a really large power of 10. So this resolves that by, so let's see. So let's do like 3 on 7. All right. So it's clean, it works. But in the other one, it would be, I would have to go to the calculator and do like, well, what's 3 on 7, and then put that in, and then because it terminates as somewhere at the decimal, it would be trying to resolve that out, and it wouldn't work correctly. Yeah, but this does work correctly because it's never doing that. So the only actual division that's occurring is it's just finding whether the current, what it views as the current numerator, is larger than the current denominator, and if it is, take that integer part. And then that's actually the part that we output. And then it saves the current denominator into this spare variable, and then it resets the denominator to the numerator minus this integer times the current denominator. And then it resets the numerator to what the denominator was. It checks if the new denominator is exactly 0. If it is, then we're going to terminate. And we come back through, and if our denominator is greater than 0, we could do this again. If it's not, then we'll just keep doing this for however many cycles are left, and then we'll drop out. And for all of these, we should always end in a t. Well, maybe not. It depends. If our integers are large enough and funky enough, then it might take more than 15. You might get more than 15 cycles out of this. But for the ones that I've tried, it's usually more like 5 or 6. So pretty much it always ends in a T. And it should always end in a T. It should always terminate, because that's what this means. This means that what comes next is unknown. This means that this stage, it was a 0, so it's 1/0 is what you would get, what this T stands for. This 3 stands for 1/3. This 2 stands for 1/2. This 1 just stands for 1/1, 1/15th, right? So T is 1 on 0, which doesn't have a value. It's not evaluable. So computation terminates at that point. But it is the correct way to do that with continued fraction. So yeah, I believe this works. It's very simple. Certainly works better than attempting to do, something like 5/7 and then plug that in, like copy that, and then like plug it in, copy and paste it, because it's just going to see this as something like this, right? And then however many zeros, whatever, there's a lot of them. It's just going to see it like that, and that means that it's not the same as 5 on 7. It's something else. So yeah, basically the reason for doing this was so that I could actually correctly get these.